Oh baik, saya nak pergi ke section 3-1 ya. Sorry, 3-3. Sorry, 5-3. Okay, what is important here is a simple theory which is known as the rate of change of a vector, yeah, with respect to a rotating axis and also with respect to the global axis, yeah, or the fixed reference frame. Okay, first, ini kita nak recall balik ya, to set up your understanding, your basic understanding. First, you must recognize there is a reference axis, yeah, capital O, X, Y, Z, yeah, which is known as the global reference frame. And then we have small o, capital O, but small x, which is known as local reference frame. Yeah. So when we have vector A, which is expressed in local reference frame, so local means, for example, we write this as using y, y, and then a, z, small k. So kita recognize kata that vector is expressed in the local reference frame. Katakan local reference frame itu is moving in space with respect to the global. So dia punya angular motion dia is given by this omega. Jadi bila kita take the time derivative, so the time derivative will be written as a dot. Dia akan ada two terms. Okay. First, mathematically, this one, plus 10 plus and then plus a x plus a y dot, and then plus a k dot. Baik. The last three terms yang ini, this kan ubah arah ada omega, so yang ini take notes. Dia berubah arah dengan adanya this omega here, Jadi it follows that from omega theorem, from omega I dot is simply equal to omega cross R, and kita ada J omega J, and we have K dot is simply equal to omega. Ini adalah hasil daripada rate of change of a unit vector, when its directions is changing or are changing, because dia adanya omega ini. Baik. So daripada sini,
Prof ada share screen.
Yes, you tak nampak? Ada nampak tak?
Tak nampak.
Dia tak nampak ya. Okay, let me re-share again. Tadi dah share. Okay, sekarang ni saya share the entire screen, senang. Okay, can you see the screen?
Masih loading. Okay.
Now we can see.
Okay, baik. Kalau macam tu saya ulang balik kefahaman ini penting sekali iaitu pertama kita nak recognize kata adanya two set of references, okay, two or reference frames, one is on me move this one. Let me move this screen. First, kita tengok ya. Ini general understanding ya. When we have any vector, kita find rate of change dia akan terbentuk daripada due to the change in direction.
Sir? Oh, sir.
Ya.
Line select. Kita orang nampak select. Jadinya cuba sir tutup kamera sir. Mana tahu jadi laju sikit.
Nak tutup kamera sudah. I really don't like about this WebEx. I think I Google Meet. It is more smooth. Screen jadi hang pula. Tengok, aduh, hai. Okay, my screen seems not to work well right now. So dia tersekat-sekat ya. Dia hang, dia tak nak bergerak pun. Sekarang hello,
Sangkut sikit.
sangkut juga ya. Mana nak turn daripada saya punya taskbar kat bawah ni. Dia kata video option ada, tapi bila tengok camera setting tak ada pula button nak turn off camera. How to switch off the camera? Right click pun does not work.
Tak pastilah Prof.
Advanced setting, turn off camera pun tak ada. Tadi masa mula-mula start, dia ada satu icon kat bawah tu yang kita boleh turn off kamera, turn off speaker, tapi sekarang langsung tak ada. And dia disappear completely. Okay, now. How about now? Is it better?
Cuba Prof ngajak lagi.
Okay. Alright. Now, first saya nak kamu nampak kata vektor A ni kita express dia dalam local reference frame. Okay, sekat-sekat lagi tak?
Okey masa. Okey sir.
Better.
Yes.
Okay, jadi saya nak padam balik ke ataupun nak continue je? Nak padam ke?
Continue, sir.
Okay. Kalau continue, first you recognize kata this vector is expressed in local coordinate. Lepas tu kita nak dapatkan dia punya time rate of change. So dia ada dua bahagian. Satunya kita panggil change in magnitude, satu lagi change in direction. So direction ni saya letak dalam kurungan warna merah ya. So change in magnitude ini is actually kita panggil dia perubahan in local coordinate. So ini kita boleh tulis sebagai rate of change of A with respect to the local coordinate iaitu small o, x, y, z. So yang change in direction ini kita menggunakan omega theorem I dot is equal to omega cross I, J dot is omega cross J, K dot is omega cross K, which at the ends after kita substitute balik ke atas tu kita akan dapat the second term ini iaitu this group here kita akan dapat omega cross A balik. Okay. Jadi hasil daripada muka surat ni yang penting ialah kita ada dua part lah ya. Okay, pertama kamu lihat due to the change in magnitude adalah ini and then due to the change in direction adalah yang ini. Okay, yang ini. So, bila kita nak dapatkan rate of change with respect to the global reference frame, in other words, it represent the absolute value or absolute quantity. So, kita akan ada rate of change with respect to local coordinate and then plus omega cross A due to the change of direction. Baik. Ini adalah persamaan yang sangat-sangat penting untuk kita move on to the next part. Baik, next part, saya nak buat macam ini. Saya nak buka skrin baru, Microsoft Word, blank, Saya nak bagi everything on this blank screen so that you can see, with at the back of our mind, that equation that we just derived, You can always refer to my class note, but instead I am just going to give you a fresh look. Fresh look. Okay. Dari segi teorinya kita buat macam ini Okay. Kita ada two cases ataupun situation. First situation ialah bila kata local dengan global share the same origin O, So, saya guna local warna merah. Baik. Bagaimana local itu bergerak in space relative to global? Baik, saya akan gunakan representasi, warna hijau lah, warna ungu tak nak lekat. That is omega of what? Of the moving reference frame, iaitu yang ini. Baik. Ini first situation that you will come across. Second situation is, lepas ni kita tengok example macam mana the two situation exist in reality. Okay, second situation or cases, you have something like this. Okay, kita ada local coordinate not sharing the same origin. So, katakan kita ada X, Y, Z at some point in space, which is A. So, this one will have its own angular velocity, omega. So, that omega is omega of the moving coordinates, A, X, Y, Z. Or I should use red color. Okay. Right. This situation can be illustrated easily. Kalau katalah kita consider, saya lukis fresh. So, situation A, let's say we have a mobile crane. Okay, let's say the center of the crane is point O, and kita ada the boom of the crane which is also centered at point O. So, kita boleh tunjukkan motion of the, yang ini kita panggil cap lah biasanya yang ini boom. So we may have this, let's say omega of the cap. Let's say kita panggil ini body number 1 or rigid body number 1 So the boom ini as our rigid body number 2 So we can denote this as omega 1, yeah, and the rate of change of that is omega 1 dot. And at the same time, kita ada, yeah, this rotation of the boom, which we may denote as omega 2, and its rate of change is omega 2 dot. So, kita boleh tunjukkan ya the two set of reference axis yang diperlukan dekat sini centered at the same origin O. So, kita boleh lukis, baik. First kita lukis global coordinate dulu, iaitu capital O, X, Y, Z. Ya. So, cara kita pilih dia terpulang kat kita. Salah satu je, okay, kita boleh pilih misalnya X kat sini, Y sini, Z dekat situ. Ya. This is global reference frame. Ya. Baik, the moving reference frame ialah, okay, saya guna warna merah. Kita boleh pilih to be coincide ya dengan global ya in this way, di mana our small x, small y, small z would be like this. Yeah. So we have O, small x, y, z as the moving coordinates. Okay, macam mana dia move in space? Dia bergantung kepada kita. Bagaimana kita pilih dia? Okay. Paling mudah sekali kita katakan kita pilih yang ini bergerak dengan omega 1. Ataupun kita kata dia bergerak dengan omega 1 campur omega 2. Ya. So saya dalam kelas kita ni, dalam nota saya discuss kedua-dua situasi ni ya. Tapi dekat penerangan sekarang saya hanya ambil, okay, moving axis kita ni kita hanya attach pada cap, iaitu rigid body number 1. Ya. Jadi X kecil, Y kecil, Z kecil akan berubah dengan omega 1. In other words, we set this equal to omega, iaitu angular velocity of the rotating axis ya, with respect to the global reference frame. Ya. Kalau kita pilih yang kedua, yang ini, maka kita punya capital omega ni adalah equal to omega 1 plus omega 2 lah. Alright. So, ini nak faham dulu situasi ya. Okay, second scenario or second cases, kita boleh consider the same crane like this, but instead the crane is designed to be somewhat more, orang kata apa, advanced sikit. Di mana, okay, the cap may have the center at point O here, while the boom may be offset by few meters right here. So kita panggil ini point A contoh. So the boom and the cap will not have or will not share the same points. So kita kata the cap still have omega 1 and still have omega 1 dots, while the boom here will have omega 2 and will have the rate of change omega 2 dot relative to the cap. So now we can choose the two reference axes. So at point O kita akan ada capital X macam ini, kita akan ada capital Y, dan kita ada capital Z. And then at point A, so okay, so you notice kata the global reference frame is set to be at point O, which is this, and then we have the local reference frame which is chosen to be at point A. So it can be chosen such that each of the coordinate axis parallel to the global, that is the easiest and simplest way lah, kan Oh, mungkin saya nak kena sebut kat sini kita tulis sikit, X is parallel to capital X, Y is parallel to capital Y, and Z, small z is parallel to capital Z. Ya. Baik. Jadi bila kita boleh pilih mereka, they are parallel, respectively. Jadi we can see easily that the transformation of the coordinate axis become very straightforward. Iaitu small I is equal to capital I, small j is equal to capital J, and then we have small k is equal to capital K. Very straightforward. Yeah. Similarly here, yeah, guys. So now we have the second moving, the second set which is moving a x y z like this. Yeah. So sama juga, what will be the angular velocity of the moving coordinate a x y z relative to the global? So here we can choose either you have it equal to omega 1, or you can choose it to be omega 1 plus omega 2. Yeah, as far as omega is concerned, omega of the moving coordinate. Yeah. Okay, we will derive the rate of change later. For now, I want you to appreciate that these are two scenarios that you may come across. Yeah. Okay, any questions so far here?
Prof, untuk second case tu, dia ada local reference LRF untuk O tak?
Tak ada.
Tak ada.
Boleh pilih, tetapi not necessary. Why we want to use local frame at O, instead kita dah ada global kat situ, dan the cap only moving with omega 1 sahaja. Whatever happened to the boom, the cap does not care. The cap tak peduli pun as far as motion of the cap. Jadi soal jawapan dia, boleh kamu ada another, orang kata, moving set of coordinate capital O, small x, y, z. Yes, but not necessary. Yeah. Boleh.
Kiranya kalau ada moving boom di atas boom tu, necessary untuk tambah lagi satu.
Okay, yes. Katalah saya lukis gambar yang ketiga lah, supaya kamu boleh. Oh, saya dengar suara saya sendiri. Yeah, it is a time lag. Okay, right. I know your concern is, okay, let's say we look at this scenario here. Let's say we consider, this is, I take it right from my class note. Okay. All right. Now, let's say we have this as the base. Let us call this rigid body number 1, yeah? So this is the electric motor, yeah? Let us call this rigid body number 2. Oh. And let's say this is the rotor, which is rigid body number 3. Okay, let us define. Yang mana satu pergerakan yang paling asas sekali? Yang mula-mula sekali? Of course, the base. Betul tak?
Betul, sir.
Baik. Kita tukarlah sikit. Kali ni saya nak yang ini sebagai X. yang ini sebagai Y, yang ini sebagai Z, ya, to orang kata enrich your understanding. So this is going to be the origin O right here, yeah. So that is global. Baik, so the base will have this rotation omega 1, betul, and its rate of change omega 1 dot. And then rotation of the electric motor, which is rigid body number 2, it will have, let's say we have omega 2 here, and its rate of change is omega 2 dot, yeah, relative to the base. And then kita ada the third angular motion, which is omega 3, yeah, the angular velocity of the rotor relative to the electric motor. Yeah, and then kita ada its rate of change, which is omega 3 dot. Okay, so here we can have two different sets of moving coordinates. Yeah. Okay, kalau kita mempertimbangkan electric motor, motion of electric motor, the first coordinate axis will be chosen such that, okay, we have small z here, we have small x here, and we have small y here. Alright, boleh? Now, so in this case, you have small x parallel to capital X, small y parallel to capital Y, small z is parallel to capital Z. Now, in order to make it a contrasting selection, I'm going to choose a second set which is going to be directed along this one. Okay, I will call this, let's say, my small x, my small y, and here is my small z. So you can see we have global capital O X Y Z. Oh, patutnya saya guna warna hitam tadi, ya. Okay, tak apa, kita tukar balik. And then kita ada the second set, which is capital O, small x, small z, yeah. And then kita ada the third set, which is capital O, small x, small y, small z. Now, can you see that in this scenario, you have two different moving reference frame? Yeah? Okay. We can choose such that for the red color, your omega can be just equal to omega 1. While the green color, you can choose it to be omega is equal to omega 1 plus omega 2. Okay? Or, if you like, this one can be chosen such that omega is equal to omega 1 plus omega 2, while this one you can choose such that it is equal to omega 1 plus omega 2 plus omega 3. Okay. So dalam kelas kita, untuk avoid confusion, saya suggest kita attach, orang kata apa, to the body of interest. So maksudnya, saya nak highlight dengan highlighter lah kot, ya. You can choose this, but I would suggest that we use this. Ya. Baik. Bila kita nak pilih yang warna merah ni sahaja, bila nak kena pilih yang merah dan yang hijau sekali? Dia bergantung kepada apa analisis yang kita buat. Kalau kita sekadar nak cari velocity and acceleration of, let's say ini kita panggil O, let's say this point right here, okay, kita guna warna hijau lah ya. Let's say the center of the disk right here, kita panggil point A. So kalau kita nak cari velocity of point A and hence the acceleration of point A, we only need to use the red color reference axis. Ya. Kalau kita nak cari, let's say the velocity of point, okay, so yang ini enough for us to use that set of reference axis. Okay. Kalau kita nak cari velocity of point B, let's say point B is located somewhere here, yeah, on the edge of the disk or rotor. So we want to find VB, we want to find AB. Then of course this one would require us to use the moving coordinate, this. Okay, so any question up to this point? So far, I don't think you are able to, orang kata, to solve the problem yet, until we look at one representation which I will do from A to Z so that you can see the difference. So far, any question about this?
No question, sir.
Okay, baik. Kalau tak ada, sekarang kita, okay, first saya nak you recognize the two different situation yang ini tadi or scenarios. Kalau you tengok dalam nota saya, okay, saya pecahkan ini menjadi, orang kata, two cases of interest. Ya, let's say kita panggil ini case 1, ini case 2 lah. Okay, kenapa kita nak kena tengok two different cases? Okay, untuk case 1, ya, senangnya kita boleh guna satu approach yang agak direct, iaitu kita panggil absolute motion analysis. Okay, absolute motion analysis. Manakala senario 2, mau tak mau kita kena guna juga di rate of change with respect to the rotating axis. Okay, terlanjur dah sampai ke sini. Saya nak lukis satu lagi gambar sebelum saya bagi example, iaitu sekarang ni bayangkan kalau kita ada rigid body on top of another rigid body. Okay, let's say we have a fixed point O here. Let's say we have rigid body number 1. Yeah. So sometimes some lecturer use the foundation of this fixed point to be rigid body 0. Yeah, rigid body 0. If you want to count it, you can use it. Yeah, the ground or the earth. Yeah, as rigid body 0. And then we have rigid body number 1. Yeah, which have the velocity, the angular velocity. Let's say it passed through point O. Like this, yeah. So I will not draw the number of other rigid body, but enough to represent you in general way. This is rigid body number, let's say we use number K, yeah. So bila tak ada garis di bawah ni, underline or kasrah, so K here is not the unit vector, it is just an index. So which may have the unit vector, the angular velocity, let's say omega K lah, omega K, passing through also the same fixed point O. So then kita ada satu point of interest on this body. Let's say this is point E. So we would like to find the velocity and acceleration of point E. And so kita kena define dia punya position of point E from fixed origin O. So that is going to be our position of point E, RE. I will write down RE, which represent position. Okay. Okay, I will erase this. I will do it one by one, step by step. Yeah. Okay, we are interested in the position. So we're going to write down, okay, for simplicity, I just write down this as R, or actually it is RE. What is vector? OE, isn't it? Yeah, vector OE, which is position of point E from the reference point O. I will represent this using a simple notation, which is RU, where R here represent the magnitude, while U here represent the direction. Okay, which is a unit vector. Yeah, unit vector representing direction. Boleh? So now the velocity of point E, which is VE, or just V, yeah, only one point kan? Oh, terbalik ya. I will erase this. Dia jadi stuck pula dah. Okay. Never mind. We just continue. Okay, we have V, or this is VE actually, yeah, which is simply equal to R dot, or RE dot, yeah. Which is, ini saya tulis ni dalam bentuk asas ya, which is OE dot. Now, what is interest on the right hand side, kita akan ada using mathematic calculus ya, it is what? Just R dot U plus somebody, can you just continue from here? What is going to be the next term?
RU dot.
Yes, RU dot. Okay. Where where U dot eraser is not effective at all ya. So tak boleh buat mistake langsung. Dia jadi apa? Jadi lembab. Okay. So U dot is going to be equal to, okay, before you can answer that, maybe kita boleh extend that line, yeah, that is your unit vector U, which indicate the direction, yeah, of point E with respect to point O. Now, we are ready to show you two type of reference axis as what we have seen tadi. Let's say X, Y, Z like this. Oops, sorry, capital Z like this. And then kita ada moving reference frame. Okay, katalah saya pilih tak nak lah kata dia in apa parallel ke ya. So katakan kita ada macam ini ya, set of reference axis X, Y, Z. like this, a small x, small y, small z. And how does it rotate? It rotates in space relative to global with this capital omega. Yeah. Jadi you will have the direction change due to omega. Yeah. Now, can you tell me what is u dot then? What is u dot? Come on, from omega theorem. Tadi kita dah sebutkan omega theorem kata kalau ada satu vektor ya yang constant in magnitude and berubah dengan adanya omega, maka kadar perubahan vektor itu ialah sama dengan omega cross that vector. That is omega theorem basically. Okay, contoh tadi kamu ingat lagi tak? Recall. If you have I dot, which is representing the change in the direction of I, kalau I berubah dengan omega, so it become omega cross I, and etc. So sekarang kita ada U changing its direction due to omega. So what is going to be U dot?
Omega cross U.
Exactly, omega cross U. Keep in mind, U tu boleh jadi dalam unit vector small I, small j, small k. So now, substitute this into here, yeah, bring this into here. What we have for this expression of the velocity is, we will have r dot u plus, after simplification, what do you get here? We get omega cross r. If you call this equation 1, this is equation 2. Boleh? Boleh guys?
Boleh sir.
Boleh.
Sekarang kita nak derive for completion iaitu the acceleration. Oh, by the way, this is absolute ya. Saya tambah sikit. Absolute. This is absolute. Why absolute? Because it is measured with respect to fixed point. Oh, now we have the next one would be absolute acceleration of point E. So this will be I need some space, so can I erase the equation 1? Ataupun I open the next page, yeah?
Open next page.
Yeah, I open the next page. Alright. So tadi kita baru saja dapat velocity of point E, which is written as V is equal to R dot, yeah, which is equal to R dot U plus omega cross R. Equation number 2 tadi, yeah. Now it follows that the absolute acceleration, this is absolute velocity, yeah. Acceleration of point E, of course, we're still talking about point E, yeah? So we write down it like this, yeah? So it is V dot actually, which is R double dot, yeah? So on the right-hand side, so let us take the time derivative of right-hand side of equation 2. What do you get here? It will be R double dot U plus R dot U dot, chain rule, and then we have omega dot cross R plus omega cross R dot. So recall U dot is what? Recall balik ya. U dot is simply omega cross U. Recall balik ya. So now we can substitute this to obtain R double dot U plus R dot omega cross U plus omega dot cross R plus omega cross R dot. What is R dot? It's equation 2 by itself, yeah? So we can substitute the entire expression, which is going to be this, which is the velocity, yeah? Now we can simplify this. It becomes R double dot U plus, I'm going to multiply R dot to the second term, which becomes this now, plus omega cross R, plus we have omega cross R dot U, plus omega cross R. Okay, here we have omega cross R dot U, and here we have omega cross R dot U. So then it becomes R double dot U plus 2 times omega cross R dot U plus, sorry, this is omega dot, yeah? Omega dot cross R plus omega cross R, which is equation number 3. Okay. In order to compare these equations, yeah, with the one used by most textbook and including some of other lecturers, let us try to interpret, yeah, these two equations, yeah, and then we put the meanings, yeah, accordingly. So, in order to do that, I need to introduce you, yeah, a concept. Okay, recall balik, this is Fig 0.0, this is rigid body number 1, yeah. And then we may have many other rigid body connected, so I will call this rigid body K once again. Yeah, so point E is located somewhere here on rigid body number K. So we define the position of point E, yeah, like this, that is our R, or you use subscript E whenever we have to deal with many other point of interest. Kalau setakat ada satu point sahaja, ya, then you may omit the subscript. Ya, dulu saya guna satu tagline, ya. Life is already difficult enough, so try to make it simple and take it easy. So between writing R or R subscript E, I guess just a simple R, yeah, is more simpler and more easier. It is understood because the only point that we are analyzing is point E. So no need to write the subscript E here. Yeah, unless saya kata tadi, if you have many different points to deal with, then of course it is wise, yeah, it is wise to use the subscript, yeah, to differentiate, yeah, which point of reference we are talking about. Okay, boleh ya? Baik. So the new concept that I would like to introduce tadi ialah the concept of, katakan dekat sini kita ada another point, let's say point E prime, which coincide with point E, yeah. But then, yeah, it is attached, ya, to the body, kan, ya, attached to the body. So maknanya dia akan bergerak dengan body K itu, ya, rigid body number K itu. So with that concept, I can now say that what is this? This is the velocity of point E with respect to the rotating frame. So tadi ingat kita ada rotating frame, okay, katalah kita lukis balik semula X, Y, Z macam ni, ya. And then kita ada global frame. Oh, dah tukar warna hitam tu. Okay, X, Y, Z like this, yeah. So the small, yeah, X, Y, Z or O, X, Y, Z is basically the rotating frame that we're talking about, yeah. So kita guna simbol, ya, sebagaimana dalam your standard textbook MB and Johnston, dia guna velocity of the point with respect to or in the local coordinate, yeah, or moving frame itu sendiri. Now, how about this? So since you have omega cross r, so as if that is the velocity of point E prime, yeah, fixed to the body. And since the body is said to have omega, katakan saya tunjukkan sini, ya, omega. So omega cross r will give that velocity of point E prime. So I will write down as this is point E prime, velocity of point E prime. Or in my latest class note, I use the term V pro. Yeah. And this one, I use the term VREL. Yes, some of your lecturer, they like to use VREL. Yeah. So, please guys, jangan rasa confused with the different term that different people use. I like equation 2, I like equation 3 because it is in its original pure form. But because you may cross-check with some other textbook, some other lecturer's work and so on. So I introduce to you the term that they use. So here is the velocity of point E relative to the moving frame, or I just use VREL in my latest version of the class note, yeah. And then we have another E prime, which is fixed to the body, and the body is rotating with this omega here. Therefore, we have its velocity given by omega cross R, or I will call that as V pro. So in my class note, the latest version, yeah, I will say that the velocity of point E will be equal to VREL plus V pro. Pro mean, okay, I need to explain to you why I use or choose the word pro. If you recall, during the pure rotation of a point, yeah, pure rotation of a point, kita ambil case 2D lah, ya. And this rotating, so that is point A, katakan, ya, that is R. And this is rotate with omega. So what is the velocity of point A? Velocity of point A is simply given by omega cross R, which is pure rotation, isn't it? So that is why I use the word V pro here, pure rotation, yeah, right here. So when you look at the expression omega cross R, it is the same terms that you have here. So that is why I use the term V pure rotation, or in short V pro. So easier for you to know, all right, the absolute velocity of point E will just be equal to V relative plus V pro. Yeah, where V relative is actually velocity of point E, yeah, with respect to or in the local coordinates, yeah. And then kita ada VE prime, which is, yeah, V of pure rotation. Any question sampai kat situ?
No question, sir.
Baik. Then jadi equation lain selain daripada yang kamu nampak ni ya, kamu akan adalah version yang VE slash frame campur dengan VE prime, macam tu ya. Baik. Saya nak padam the last line here because we need the space.
Sir,
Ya.
omega cross R tu adalah absolute velocity lah untuk satu rigid body tu. Oh, okay.
Okay. Baik. Next, let us make sense of these terms in equation number 3. So, this is the acceleration of point E relative to the moving frame, which some textbook call it A rel, ya. Maknanya acceleration of point E with respect to the moving or rotating coordinate frame. That is why they call it A rel, yeah. The second term here is known as the A Coriolis. So in short, they just write in as A core, yeah, Coriolis. So you can refer to the names of Coriolis like this, yeah, Coriolis acceleration. So look at the form. It is 2 omega cross R dot U, where R dot U is what? VREL actually kan, ya. Kalau ingat balik, R dot U here, right here is VREL, ataupun VE relative to the moving frame. Yeah. So take note, this is actually VREL or VE relative to the moving frame. Now, look at this form, the last two terms here. So, for the last two terms, I want you to recall, dekat sini, remember the acceleration of point A will have what? What is acceleration of point A? Can any one of you recall? Guys, what is the acceleration of point A for this pure rotation? Okay, how many of you recall here? Acceleration of point A is given by what? Omega dot, which is alpha kan, cross R plus omega cross R. Betul tak? So you'll have the tangential component and then you have the normal component. So kalau recall balik, this is the A normal kan? Sorry, A tangential, and while this one is A normal. Ingat balik tak? Jadi kalau you tengok term yang di sini, this one, compare dengan term yang kita ada kat sini, exactly the same term, isn't it? So, we will write down this is going to be A of the point E prime, or I use the term E pure rotation. Yeah, A pro. Therefore, we can write down the expression for the acceleration of point E, which is the acceleration. A is simply equal to A rel plus A Coriolis plus A pro. Or compare this with some textbook, B and Johnston, for example, it will be written as E relative to the moving frame plus A Coriolis plus A of the point E prime fixed to the body. Right. Are you ready for the example? Okay, I'm going to give you, let's say, 10-minute breaks, and then we will cover one example. The other example, I will just ask you to go through the class notes. I have a lot of example presented to you in the class note. Yeah, just make use of them. Yeah. All right. So take 10-minute breaks. Yeah? We will come back around 4:24. Yeah, 4:25.
Yes, sir. Thank you.
Okay, welcome back. Okay, let us look at this. Okay, I'm going to give you, let's say, example one. Okay, let us look at example one. let's say we're going to consider a mobile crane, the one that we just had in the introduction, earlier. All right, let us have the simplest case where the design is such that the cab and the boom, have same reference O, as the origin. So this is point O, this is the boom, So the cab is rigid body 1. Oh, by the way, you may have the situation where the entire body, of the crane may be moving, So we can call this as velocity of the crane, and you may have the acceleration of the crane, like this. Okay, let us now consider the motion of point A. Let's say we have X, Y, Z like this. Now, to get started, let us choose such that, small x, small y, and small z, are parallel to capital X, Y, Z respectively. So the cab, will have the angular rotation or angular velocity omega 1 like this, and its rate of change, let's say we have omega 1 dot. Let us give some values. Let's say this is equal to 2 radian per second. And let's say it is increasing at, let's say, 5, decreasing, radian per second squared. So let me say this is decreasing. Decreasing. Now, while the boom, the boom will have, I'm going to use, maybe I can draw the boom using different color. Let us redraw this. I'm sorry, my drawing using this is not that nice. So the boom may have the angular rotation, omega 2 like this. Okay, what is the value? Let's say 3 radian per second. And then its rate of change with respect to the cab is omega 2 dot. Let's say this is equal to 4, radian per second and per second squared, and is increasing here. Or I will say increasing omega 2, This is decreasing omega 1. Right. So we would like to perform, part A, determine, we need to give values for the length of the boom. Okay, let's say the length of the boom is 15 meters. 15 meters. Okay, part A, we would like to find the absolute angular velocity of the boom, OA. Hence, angular acceleration juga, absolute angular acceleration. Part B, we would like to find the absolute angular, bukan angular lagi. The absolute velocity and acceleration, of tip A, on the boom. Right. Okay, analysis or solution. So first stage kita dah ada iaitu reference axis ya, kita ada, okay, take note, kita ada capital O, X, Y, Z as our global reference frame ya. Dan kita ada ya O small x y z as our local reference frame. Now for this we have to choose how you want to choose the rotation of local reference frame. So we are going to choose such that omega is going to be equal to, I'm going to have the absolute velocity, angular velocity. So I will choose this one here. Omega of the rotating axis is going to be consists of omega 1, which is omega of the cap, plus omega 2, which is omega of the boom relative to the cap. All right. So the absolute angular velocity of the boom OA. So we see that boom OA is mounted on the cap, which is rotating at omega 1, while the boom is rotating at omega 2 relative to the cap. Therefore, for part A, we will say omega of the boom, which is absolute, is going to be equal to omega of the cap, which is omega 1, plus omega of the boom relative to the cap, which is omega 2. So let us express this. This is going to be omega 1. Okay, what is the direction of omega 1? It is going to be positive z. So I'm going to use local coordinate first. So I will have small k and then plus omega 2. You can put the numbers later. That is going to be small I. But then kita kata, since small k is equal to capital K, and then we have small I is equal to capital I, for the reasons small x parallel to capital X, small z is parallel to capital Z. So you can write down the reason on your own. So finally, or eventually, we can express the answer to be as 2 capital capital K plus 3 capital I radian per second. So that is the absolute angular velocity of boom OA. Second part, alpha, which is absolute angular acceleration, of the boom, which is basically omega of the boom dot, So using calculus, so the derivative become omega 1 dot K plus omega 1 K dot plus omega 2 dot I plus omega 2 K dot. Now look, omega 1 dot is given by here, 5 radian per second. But then, since you have the term decreasing omega 1, so when you substitute the value for omega 1 dot here, you must have the negative signs because it is opposite to the direction of the velocity omega 1, angular velocity omega 1. So we'll take note on that later on, keep in mind. But now let us look at the term K dot here. So look at the z-axis, yeah, on the crane, sorry, on the cap. Whatever or however the cap rotates, yeah, the z-axis is maintaining its direction as far as the cap is concerned. Yeah. So for this part, k dot will be equal to 0. No change in direction of k, yeah, for cap. Hey, although I hate to make this kind of mistake, yeah, it is not k dot, it is I dot. I don't know why I write k dot right here. It is supposed to be I dot. Okay. So, where we can write down here, where I dot. So since we choose to be like this, yeah, so you can write down, this is going to be omega cross I, isn't it? So that is going to be omega 1 small k plus omega 2 small I cross with I. So what do you get? So I always encourage students, yeah, to perform the cross product by arranging unit vector like this, yeah. And then you put the cross sign, yeah, in between, and then indicate the positive sense of the cross product. So we have k cross I. So we have k cross I give you positive j. So you have omega 1 here, and the cross product of k cross I is going to be j, so you have omega 1j. And then the second term, you have omega 2I cross I, that will be 0, so we have 0 there. So now you can substitute the terms accordingly. So I'm going to have omega 1 dot k plus 0 plus omega 2 I plus omega 2 times omega 1 j. So now let us put in numbers. Omega 1 dot is going to be negative 5, yeah? So you have negative 5 capital K. Now you can use the global coordinates straight away. And then we have 4. We can use global coordinate, capital I, plus, now omega 2 is 3, omega 1 is 2, so 3 times 2 is going to, okay, let us write down 6 here. This is 3, this is 2 here. So 6 capital J radian per second squared. That is the absolute angular acceleration of the boom. Right? Okay, now let us move on for part B. Any question?
No problem.
No, sir.
Okay, kita pergi kepada part B. Boleh tak kalau saya introduce dekat sini, kat gambar rajah ini, point A prime, iaitu the point which is as if, yeah, fixed to the boom, yeah, coincide with point A, yeah, at the same point. It is fixed to the boom, it is coincide with A. Right. Let us go to the next page. All right. So part B. Okay, before we write the answer or solution for part B, I just want you to recall the theoretical part, yeah, that we have position written as R, which is RU, yeah, velocity V, which is simply R dot, yeah, which is equal to R dot U plus omega cross R, yeah, and then acceleration, which is V dot or R double dot, yeah, which is equal to R double dot U plus Coriolis acceleration, which is 2 omega R dot U plus omega dot cross R plus omega cross R. Okay. Ini kamu kena ingat ya. Sama ada dalam bentuk original form yang ini ataupun dalam form yang kamu dah ingat itulah, iaitu V is equal to V real plus V pro, ya. Acceleration A real plus A core plus A pro, ya, up to you, whichever sense, whichever orang kata equation that you want to use, ya. I like to use the original and pure form, yeah, which is this one right here. So let us write down the position of point E. Sorry, position of point A, yeah. So we'll just write down R, which is going to be equal to, let me just use a symbol, yeah. I like to work with a symbol somehow, yeah. So let's say this is L, yeah. OA is equal to L, yeah. So I'm going to write down this is L times unit vector U, yeah, where we can resolve U, yeah, into local coordinates. Okay, I have to give you the angle here, theta. Let's say theta is equal to inverse tangent of 3 over 5. Sorry, 3 over 4, yeah, theta, the angle. So when you are given the angle like that, yeah, you have to configure what does it mean. So it means that the opposite is equal to 3, yeah, the adjacent is equal to 4, and the hypotenuse is equal to 5. So then you can see that sine theta is simply 3 over 5, yeah, or 0.6, while cosine theta is 4 over 5, which is 0.8. So now we can express U, yeah, using local coordinate. It will be what? Cosine, cosine theta small I, and then plus sine theta small j. No, small k, yeah? Small k, yeah, because here is k direction. Or small z direction. Oh, sorry, this is j, yeah? I make a mistake twice, yeah? This is j, small j. Okay, any question for this part? R is simply LU, yeah, length L, and then unit vector is U. So if I ask you to show what is the direction U is along OA lah. So that is the unit vector U, yeah, along OA, which is UOA itu sendiri, yeah, along OA. Okay. Then we write down the velocity of point A. So just V. So R dot is 0. Why? Because there is no change in the magnitude of R. Yeah. Bilakah R dot is not 0? if you have a telescopic arm OA, yeah, telescopic arm OA ni macam ni. Sorry, my drawing is too bad. Let me erase this. Yeah? I don't like my drawing. Okay, telescopic arm. Oh, yeah, I'm sure you have seen this a lot. Yeah, in the actual design. Yeah, whenever you see construction. So that is point A. So this telescopic arm means that this point will move, yeah, with some velocity and have its rate of change. So maybe we can use the symbol, let's say, we can use P and then we can use P dot, yeah, to represent its rate of change, yeah. So this one would be unit in meter per second. This one would be meter per second squared, yeah. So you can see that R dot here represent a change in the magnitude of vector OA, yeah. So in this case, you have R dot equal to P, yeah. But in our present case, yeah, R dot is 0 because arm OA is fixed. So then, what is omega? Omega is already given here. Yeah. So R already defined here with U given by this equation. So we can now just substitute this into the X equation. So what we have is just omega 1 plus omega 2, yeah, cross with L time cosine theta J plus sine theta K. So omega 1, omega 2, which is omega of the boom, by the way, is just equal to, yeah, this one. So since we have all the x's, so maybe I should write it somewhere here. Okay, kat mana nak tulis? Okay, kita pun dah tulis kat sini tadi sebenarnya. Okay, kat sini ya. Ni. Not only that, small j is equal to capital J, kan, yeah? So you can work on with this, yeah, by substituting small j with capital J, small k with capital K, and so on, yeah. So you can just perform the cross product. You want me to show one line here, or you can configure it on your own? Or maybe for the sake of solution. So let me just write down. This is going to be, I'm going to use global coordinates. So you're going to have 2k here plus 3i here, cross with. Now L cosine theta, L is 15. Okay, cosine theta that is 0.8. 15 times 0.8. What do you guys get? 15 times
12, sir.
Yeah.
Sir,
Apa?
12.
Okay, you get 12. And the unit vector small j can be replaced with capital J now. Plus L sine theta, which is going to be what? 9, isn't it? Okay, the cross product. So you have 2k cross with 12j, sama ya kan, ya. So you have k cross j, terbalik, opposite, ya, k cross j. So you get what? Negative I, right? So you get negative here. Unit vector is going to be I. And then you have 2 times 12, which is 24. Okay. And then you have 2k crossed with 9k, which is 0. So no need to write. Next would be 3i crossed with 12j. I cross j is give positive k. So we have plus 36k. And then we have I cross k. I cross k give you negative j. So then you will have minus here. 3 times 9 is 27. So negative 27j. Okay. The unit would be meter per second. That is the velocity of point A, yeah, on the tips of the boom. Dalam example, saya memang arrange the final answer to be in the order of X, Y, Z, ya. So maksudnya dekat sini kalau boleh you susunlah dalam order yang X, Y, Z, iaitu komponen X dulu diikuti oleh komponen Y yang ini, diikuti oleh last kali komponen Z. So macam ini, ya. Okay, try to arrange it in the order, yeah. Okay, any question up to that point? Baik, kalau tak ada, the next 9 minutes or so, we are going to compute the acceleration, the absolute acceleration of the tip A on the boom OA. Let's see if I can reduce this further. Can you see clearly if I reduce this font size to smaller size like this?
Yes, sir.
Boleh, ya? Okay, baik. Okay, yang ini sebelum kita proceed to acceleration, saya nak tulis juga kat sini, ya. Take note bahawa R dot is equal to P here, yeah, and R double dot is equal to P dot here, yeah, with the given magnitudes or given units, yeah, meter per second squared. So next would be the absolute acceleration. So even though I did not write down the word absolute, but it is absolute here, yeah? So just write it down. So next we have absolute acceleration, yeah, of point A or tip A, yeah. So recall the equation. That is the equation here. So we're gonna write A is equal to, I just copy that down, yeah, R double dot U plus 2 omega cross R dot U plus omega dot with cross with R plus omega cross R. So in our present case, this is equal to 0. In our present case, this is equal to 0. Yeah. So there is no Coriolis acceleration here. So we have omega dot. What is omega dot? This is omega of the boom, isn't it? Sorry, alpha, yeah, alpha of the boom itself, the absolute, yeah, which is what? Given by this, yeah. Yeah, given by that. So the rest of the term you already have, yeah. So we can just bring the result. Okay, by the way, what is this? That is the result of that, isn't it? Here. Omega cross R is already obtained up here, yeah, from this equation, which we already performed. Yeah, we have that negative 24i minus 27j plus 36k. So we can perform the cross product. So that would be, I'm going to arrange that in the order of I, J, K. Yeah? So I will have 4I plus 6J minus 5K cross with R, which is 12J plus 9K plus omega, which is mana tadi omega, ya 3I plus 2K, ya 3I plus 2K cross with this one, which is minus 24I minus 27J plus 36K. All right. You can see, even though the first two terms on the right-hand side are 0, yeah, but still you have a lot of work to do, yeah, in terms of cross product. Let me give you the tips for your ODL exam 2, yeah. Let's say this is, let's suppose, yeah, this is your test question. Up to this point, yeah, you know how to obtain the correct how to write the correct expression and how to obtain the corresponding terms in each of the quantities, yeah. So if you do not perform, yeah, until the end to obtain the final answer for the acceleration, yeah, if you did not do that, yeah, at most I will just minus or deduct, yeah. I'm telling you this, yeah, to all of you. At most, I'm going to deduct -1, yeah. If you keep on performing this, it may consume a lot of your time. Maybe you need a minimum of 5 minutes here, or some of you may take even 10 minutes, yeah, just to get this cross product done. So if you were to be smart, yeah, follow this tip then, yeah. Why bother of spending, yeah, extra minutes, yeah, for worth of 1 point, yeah. Dengan syarat, apa syarat dia? Syarat dia at least during the previous step, which is right here in the calculation of the velocity, you have shown me, yeah, you have proven to me that yes, you know how to perform the cross product right here, yeah. You have shown me this. You got this answer correct, at least for the velocity. Yeah, you get this expression or terms correct. Then I know you know how to perform the cross product. It is just a matter of time. Yeah. So I would say, if you are smart, you just write down, okay, this is equal to, yeah, continue, yeah, the calculation to obtain, yeah, final answer or the final answer. So let's say this, ayo, guys, it is gone. The whiteboard is gone. It is closed already. Hello, are you guys still there?
Ada problem.
Yes, sir, still here.
I'm still here, sir.
Okay. You faham tak tip tadi?
Faham, sir.
Faham?
Jadi, you dah bukti kat atas masa calculation of velocity kata you boleh perform cross product ya dengan betul. Jadi dekat bawah tu biasanya dia involve a lot of cross product ya. Sometimes you have 3 by 3 lah ya. Or at least 2 by 3 macam tu kan ya. Then I know lah kata you dah tahu macam mana nak perform. It's just a matter of time. So try to be smart here ya. Make it simple ya. Take it easy ya. Our tagline ya. So kalau kata 15 markah hilang satu markah, you still have what? 14 out of 15, isn't it? Rather than you spend 10 minit lepas tu masa tak cukup untuk nak solve next problem or next question, you hilang lagi banyak markah kat situ. Okay, that is the solution for the example. Yeah. Come next week, I will spend maybe another half an hour to give you the second scenario, the second situation. Yeah. When you have the moving coordinate is not sharing the same origin as the global coordinates. Yeah. But meanwhile, I encourage you to look into examples that I have in my class note. There are plenty of them. Yeah. Maybe I'm going to prepare you a set of Google Classroom quiz using Google Form where you have to answer that quiz to test your understanding sometime this week, or no, maybe maybe tomorrow or maybe Monday. And so I will ask your respective lecturers to just share with you in your own Google Classroom. Okay, any questions before I end my lecture here? I don't know. Saya tak tahu apa yang saya tertekan tadi sehingga dia tutup semua sekali. Okay, kalau tak ada soalan, we end our class right here. Yeah. So maybe ialah kita hilang 1 jam tadi kan? Oh, 1 jam lebih ya. Mungkin saya akan buat satu video, short video to cover one more example, and then I will share it to you. Yeah, you can see it. Yeah, in order to make up for that 1 hour lost session. Yeah. All right, guys. So I see you next week. So next week mungkin kita akan spend half an hour to wrap up everything in kinematics of rigid body, in 3D, and then the rest we will spend time for kinetics, of rigid body.
Okay, sir.
All right. For my group, please answer the attendance, For groups 8B, please answer the attendance.